Welcome everyone, and thank you for joining us for today's webinar. My name is Laura Roberts, and I'm the Ava Marketing Manager at PDS Group. For those of you who may not be familiar with PDS Ava, we build cloud-hosted software which addresses key limitations in existing reservoir modeling workflows. One area that we believe needs a little more attention is structural geology modeling. In a given reservoir, how sure are you about how far faults extend in your reservoir and whether they connect or not? What impact does this uncertainty have on field development planning? Reservoir compartmentalization is a major uncertainty in the appraisal of petroleum reservoirs. Poorly understood reservoir compartments and the connectivity of reservoir faults affects the volume of movable oil and gas in a given field and can have a serious impact on field viability and profitability. Over the next half hour or so, we'll showcase how Ava Structure, our new plugin to the Petrel E&P software platform, allows you to assess the impact of fault connection uncertainty by generating alternative plausible fault scenarios. We'll kick today's session off with a little housekeeping and then jump straight into the presentation. We've set aside some time at the end of the webinar for questions and discussion. If you wish to ask a question during the Q&A part of the webinar, you can type them in your GoToWebinar control box in the question box. Or alternatively, if your question requires a little more explanation, you can use the raise your hand function, and I'll turn on your microphone so you can ask the question verbally. We're also really keen to hear your thoughts on uncertainty and structural modeling, and in how you use structural modeling in your workflows. So we'll run a couple of polls throughout the session to gather your views and kickstart our discussion. Today's session is presented by Dan Hemingway, the newest member of the Ava team. Dan is a senior geologist who is currently supporting the development of Ava Structure, as well as lending a hand with our other products, Ava Clastics and Saturation, on an ad hoc basis. Dan joined PDS Group about a month ago. He has an MSc in structural geology with geophysics and a BSc in geological sciences from the University of Leeds. Post-graduation, Dan worked at RDR, based in Leeds, which is now part of Schlumberger, as a consulting structural geologist and production specialist and champion. More recently, Dan has held roles as a senior geologist and a lead geomodeler at RPS Energy, based in London, where he spent the past 5 years working as a subsurface technical consultant. So, without further ado, I'd like to turn the timer over to Dan. Thank you, Dan.
Okay, thank you, Laura, and thank you all for joining us this afternoon. What I'm going to do is I'm going to go through a few presentation slides just to start opening up some discussion towards uncertainties in the subsurface, and then specifically some structural uncertainty. And then I'm going to go into Petrel and run a live demo using Ava Structure. So let's just start then by looking at how we typically handle subsurface uncertainty within our geomodeling workflows. What we tend to do then is identify what we believe to be the key uncertainties relating to our reservoir and begin to build up multiple reservoir models or individual scenarios that we capture what we believe to be that reasonable range. We tend to isolate an individual parameter, such as things like net to gross or porosity, and we build in a range of possibilities of that variable, perhaps defining a distribution and identifying things like P10, P50, P90, and building our uncertainty around that range. Now, typically, when we're doing this, these uncertainty workflows are anchored to single case structural models or a base case. And by this, I'm referring to the structural configuration of our faults, the horizons and the fault compartments that are produced from this. And then from this, we build in workflows to tweak and modify the internal reservoir parameters with relative ease. And I say relative ease because I'm comparing that to the ability to build these structural models in packages like Petrel. And the reason for this, obviously, is because to build up and generate these structural models is typically an onerous task, taken from the seismic interpretation phase through to the modeling phase and through processes such as pillar gridding. We know that they can often be quite painful, quite laborious, and they take a lot of time to get them right. So in this webinar, then, we're going to demonstrate how this structural uncertainty can be routinely incorporated into this geomodeling workflow, essentially present a way of building very quickly multiple realizations of the same seismic interpretation, but as a structural model, configured differently with different fault compartments and connections within our reservoir, and integrate this into the full uncertainty work cycle. Okay, so when we consider uncertainties in the subsurface, we tend to broadly group them into two themes, those being the in-place volume and the recoverable volume. So just starting at the in-place volume then, we're looking at two things basically, the gross rock volume and the hydrocarbon volume. So the GRV we're essentially defining as the tanks. How big is our reservoir? Uncertainties that come into play are things like the horizon interpretation, the fault position, so the quality of both of those, the interpretation domain, but also things like the depth conversion. What is the uncertainty associated with velocity modeling, etc., and also the fluid contact. So how does the tank change based on these uncertainties, and how sensitive is that tank to these variations in any of these parameters? Now, the second thing in here, the hydrocarbon volume, obviously, we're looking at that internal petrophysical makeup of our tank. So how does the net to gross change? How does the porosity change based on things like Fash's distribution and our geological model? And ultimately lending itself to water saturation and the implementation of a saturation Howard function. So those two main components comprise our in-place volume. And once we have that, we have a good handle on how uncertain our total volume within our field is. Now, the second thing we refer to then is the recoverable volume. And we're looking here at the movable volume of oil and how we can get that out of the ground. We're talking about things like relative permeabilities, aquifer support or pressure. Obviously, the in-place volume is an uncertain factor associated with this. But what we're going to look at today specifically relating to the structural configuration is the fault connectivity and the well count, and how we can develop a field based on things like the number of well and the cost involved, etc. Okay, so then moving away from sort of general uncertainties with our modeling workflows and looking specifically at structural modeling, how does structural uncertainty then impact our models? And again, I've categorized it into those two main categories, the gross rock volume and the connected volume. So again, the gross rock volume, the tank, how does that total rock volume estimate change by varying the structural configuration of our model? And typically what we do is we flex the top surface, we flex the bottom surface, and we move the faults around a little bit. But it's all relative to that interpretation. We're taking that main tank and just flexing it a little bit to see how sensitive it is to things like velocity modeling, uncertainty, and seismic interpretation uncertainty. But more importantly, what we're concerned with is the connected volume. So how much of that total in-place volume then becomes movable between the fault compartments? And traditionally, what people tend to do is look at the juxtaposition of the reservoir and the fault zone analysis. So they take that single base case, that single configuration of our fault compartments, and look at how the reservoir is connected across the fault there. And if you see reservoir across reservoir, you can then take it a step further and do fault zone analysis. But this is all assuming that single base case is correct. The main uncertainty, and this obviously comes before any of the juxtaposition analysis or any of the fault zone analysis, is making sure that that geometric architecture of the fault network is correct. And so here we're talking about how does the number of compartments and how does the connection of the reservoir across the faults rather than within the internal sand units across the faults change as we start to produce. And obviously, why do we care? So in terms of the gross rock volume, we're interested in what is the total amount of hydrocarbon in place. And from this, we can start to build up an idea of whether it's going to be economic to produce a field, the number of wells that are going to be required, and actually where we're going to place them within our field. But that also plays into the connected volume. So again, once we have that oil in place, how easy is it going to be to move it between our fields? How's the sweep going to be affected by things like compartmentalization, the localization of the flow around the low flow tips of the fault, because that's essentially where we see the reservoir connected with the greatest area across our fault. And ultimately, this all lends itself to the number of wells and the placement of those wells. Obviously, lending itself to ultimately costs. So what we're going to demonstrate throughout this webinar is how we can use Ava Structure to get a handle on this connected volume uncertainty at a very early stage in the workflow. So we're not taking it all the way through to modeling and then running the uncertainty there. We're running the uncertainty analysis to do with the compartmentalization and the well placement and recovery based on our interpretation data. Okay, so that brings us into the first poll of the webinar. So I'll hand you back over to Laura.
I'll launch the poll now, and you'll have a couple of minutes to cast your vote. The question in this poll is, what do you consider to be the most important when calculating total field recovery? I can see there's still a couple of webinar attendees who haven't selected their choice. So please go ahead and do that now, as I'll be closing the poll in the next few seconds. So thank you to everyone who has voted. It's the most popular choice is in-place volume range. That seems to matter the most when calculating total field recovery. But the connectivity of reservoir sands is just as important as the number of fault blocks and the well count. Attendees didn't think that the KV-KH ratio or other engineering parameters such as relative permeability and aquifer support were as relevant. Thank you to everyone who took part.
Okay, that's very interesting to see those results there, and hopefully as we work through the rest of the webinar and have a bit of discussion at the end, we can bring in some of the issues relating to the connectivity and the well count at the end of the presentation. But for now, I'm just going to move through and just start a little bit of discussion about the resolution in the subsurface. So another 5 minutes of slides, and then I'll jump into the Petrel demo. So what I'm representing here is typical horizontal and vertical resolution. So when we're in the seismic domain, we're restricted by two things really. We've got the vertical seismic resolution, so that being at what resolution do we start seeing tuning effects between our reservoir sands. The acoustic impedance, when does that start interfering with beds that are sort of thinner than the seismic resolution, and we can't really pick out our horizons or our faults? And that tends to be at around the 20-meter mark. I mean, I'm using averages here, but let's just say 20 meters on average. And obviously the horizontal seismic resolution, here I'm referring to things like bin spacing. So we have this window below 20 meters vertically and below sort of 12 to 15 meters horizontally, where we're not accurately mapping the complexities in the subsurface. So our seismic interpretation domain sits in here. I've included 2D here because obviously we can maybe have a horizontal spacing that's sort of up to sort of 50, 100, maybe even a kilometer spacing apart, but again, still limited by that vertical seismic resolution. We build into our static model. We start looking and integrating our log data, and that's obviously at a much finer scale, which is why it sits below that seismic resolution. So we can start layering up our model to sort of a meter, maybe half a meter, but our horizontal resolution, again, based on the computing power and the ability to model these things by the number of cells in our reservoir models, that increases to sort of 50, 100, maybe 200 meters. And then obviously another episode of upscaling. So from the seismic interpretation domain to the static model, then up to the dynamic model, we upscale horizontally, we upscale vertically. So we're back up to sort of between 10 and 20 meters on average for our reservoir models, and that horizontal spacing has also increased too. But as geologists, we know that we have geological complexities that exist both below these resolutions, but also sort of in the bridge between seismic interpretation domain, static model, and the dynamic model. So the questions that we always need to keep asking ourselves when we're building our model is, what are we trying to represent? What are the important parts of the geological complexities that exist below the resolution, but also those geological complexities that we are actually trying to model within both our static and our dynamic models. And just to touch on what we're actually imaging then, we know that we don't actually image the faults. We tend to interpret faults and diagnostic indicators, such as the reflector terminations, caused by the high angle intersection of that fault with the seismic wave. So as the seismic wave propagates down through the subsurface, the angle at which it intersects the fault means that we tend to just see chaos and noise around there. So what we're relying on is those lower angle horizon reflectors and to give us an idea of where that fault is. Add to that issues like Fresnel zone imaging and attenuation of that seismic wavelet at and around the fault zone, we obscure what we call the image of the fault even further. So therefore, and inherently to the process, those parts of the faults that exist at or below the seismic imaging resolution are not mappable using those conventional interpretation techniques. So we know that it's an issue, but the question is, how do we account for this uncertainty when we're looking at building up our reservoir models? And obviously those parts of the faults become very important when we're looking at both the structural configuration, so in terms of compartmentalization, how well is our reservoir connected structurally throughout the field, but also things like sweep predictions and where the flow is going to be localized, because at the lower throw parts of our faults is where we see the most reservoir connected typically, and we can use that as a prediction as to how the reservoir will produce and behave. Okay, and just a bit of perspective on that then. I've just taken 3 different outcrop images at different scales and placed a typical seismic wavelet on there. So let's say that's approximately 20 meters. In the vertical scale, what are we actually mapping here? We're probably picking acoustic impedance contrast in here and maybe in here somewhere, but we're never actually going to map the internal architecture of that fault. Similarly, on the horizontal scale, again, this is about 15 meters across in here. That's one bin spacing in our seismic data set. What are we actually capturing in here? You can see this, the deformation here is being accommodated by multiple slip surfaces, whereas in our seismic profile, we're probably going to see this as either a single reflector, if at all, or a slight little bump in our horizon. And it's these sort of lower throw parts of the faults that can really work up and build up a connection within our reservoir, as a structural connection rather than a sand connection. Then even down to the centimeter or meter scale here, this is a fault core. We don't need a lot of deformation to create a significant seal over geological and production time. Cataclases can exist on very low throw faults, depending on sort of depth of deformation, etc. So being able to identify where these low throw structures are becomes, again, very important. It's not just the extent of the fault throw, it's how they're connected up. And we know that these structural complexities cannot be captured. We know that the low throw parts of the faults are not resolvable in the seismic data, but we know that they're important. So the result of that, obviously, is that our seismic interpretation is inherently uncertain, and that we have variable possible structural configurations that will be possible within the resolution of what we call our base case interpretation. So just looking at these images, how many different variations of these structures could you expect to have within this seismic wavelet? And that's what we're trying to capture. Okay, and just an introduction to fault throw profiles. Obviously, we know there's uncertainty, and one of the ways that we can start to address things like fault tip extension is looking at fault throw profiles. And this is an example here of the relay ramp in Arches National Park in Utah. And what you can see is that we've got two main faults that are dipping towards us. We've got a footwall and hanging wall cutoff in here, creating this soft link between our two fault segments. So essentially, if we're trying to flow up through this reservoir, we can do so with relative ease. There's no hard link within here that's causing our faults to be linked within there. But what we need to consider here then is the seismic wavelet relative to these set of faults then. Again, this is, let's say that's 20 meters. We need to ask, what are we actually mapping? We're looking for the acoustic impedance contrast between the reservoir and the overburden or the underburden. We can probably pick that pretty well as we follow the cutoff here until we get to around that tuning thickness, where we're going to start seeing interference between the reservoir, both on the hanging wall and the footwall side. And this is what we define as our seismic fault tip. We say that basically anything towards the fault tip end of this fault in here is not going to be mapped within our seismic. But we know from our field observations, specifically in this case, that our true fault tip exists here. So we have one in both fault structures within here. And the question is, how do we project from our seismic fault tip either to our true fault tip, and where does that exist within this zone of uncertainty? This is what we call the process zone. And essentially our true fault tip, depending on how that fault is developed, could exist anywhere within here. And that is the main uncertainty. We want to know if this true fault tip is perhaps interacting with this fault in here and creating a hard link, or where it extends within our horizon interpretation. And we can do that using things like fault throw profiles to get an understanding of how that's happening. So again, just mapping the fault throw as we move along here. We take a throw sample point at each one of these spacing intervals, and we hit the seismic fault tip in here. And you'll see that that roughly corresponds to the seismic imaging resolution of about 20 meters. The question then is, how do we project that seismic fault tip to our actual fault tip within a region of uncertainty? And that's what we're going to look at using Ava Structure to do. But before we get there, just a quick another poll, essentially using that theory of fault tip extension. There's this fault in here, just south of the production well A, and based on the fault throw profile in here, the poll asks, how far would you extend the fault tip to the west? So in this direction, how far would we extend this fault tip? So you can choose between 200 meters, 200 and 500, more than 500, Or if you haven't used these before, just select I don't know what you're talking about. And we'll come back and look at this in a few seconds.
So the new poll should be coming up on your screens very shortly. Please go ahead and vote for your preferred choice as to how far would you extend the fault tip to the west. There's a few of you who still haven't cast your vote. So if you haven't, I'd encourage you to do so in the next few seconds, as I'll be closing the poll very soon. So the overwhelming majority, Dan, believe that they would extend the fault tip to the west by 200 to 500 meters. And one of our attendees didn't really know what you were talking about. The other two options, less than 200 meters and above 500 meters, didn't receive any votes at all.
Okay, that's great, thank you. Now, just before I discuss the results then, I'm just going to point out, those familiar with Petrel will notice that this map here comes from a model. It's a pillar gridded model. So you can tell that we've already been through the modeling domain or the modeling process and got there to produce this fault throw map. And I'll come and look at the results of that in a second, but just to touch on what we're doing when we're modeling. Now, once we've taken that uncertain seismic horizon interpretation, we apply iterations of smoothing, both to the fault and both to the horizon. So you can see in the images here, what we tend to do is build through our faults, and then we say use an arbitrary step out distance, and we remove all that data, all the noise away from there to make sure we get nice hanging wall footwall intersections. And what that's actually doing is removing the hard data, is removing what we know to be the true fault throw. And we're using some sort of extrapolation away from the fault in order to capture that. The next phase of smoothing comes through when we apply our gridding. So you can see I've just put the grid cell resolution on here. This is actually a very fine grid. This is about 50 by 50 meters, but you can see all the data that's being removed away from here to get that nice clean intersection when we're using pillar gridding. So the point of this is just to demonstrate that when we're calculating that fault throw, and the fault throw profile that we just saw there previously was actually calculated from the modeling domain, where we've already undergone these smoothing effects. So what we can do with our fault tip extension, if any, is apply these automatic extensions. You can see I've just taken a snapshot up here from Petrel structural frameworks, where we just give an arbitrary number in here. And these apply uniform extension, it's arbitrary, and it's not based on anything geologically sound. We can do this manually, but as I've just demonstrated with that model, we've already applied those efforts of smoothing, which have taken away the hard data. It's taken away the noise, but it's taken away the data that we need to calculate that fault throw. So the answer of 200 to 500 was actually better than the first one, obviously 200 meters, because we've applied that smoothing. But what we're actually looking at is something like this, and it's more than 500 meters. In this case, this fault actually links up to this little kink in the fault in here. This is a displacement anomaly in this fault. It actually shows that this fault here is extending up over 1,000 meters to a kilometer from in here, and we could see that from our interpretation data. Whereas looking at a fault throw profile in here in the modeling space has already taken away and smoothed out the information that we need to get a valid result in here. Okay, so I'm just going to jump into Petrel then and just demonstrate how we can use Ava Structure to quantify some of those uncertainties and understand how uncertainty both in interpretation and fault tip extension can be integrated to build up structural configuration models. Okay, so I'm in Petrel 2018 here. I can access Ava Structure by selecting from the Windows menu in here, or I can use it from the Ava ribbon in there. So as with our other products, I can just select Ava Structure and it opens up as a new window in here. So this is my landing page. It's got things like tutorials, a video, and things to help me guide through my interpretation. But I'm just going to build up a new interpretation then. In here, I'm just going to call this Structure Demo 1. And to get it going, I'm just going to add in my horizon interpretation here and a folder containing all of my faults. So let's just get that going. Okay, so in terms of input then, obviously I put in my horizon interpretation and a folder containing my faults. What Ava Structure is doing now, and what I need to specify here is a number of cases. And what this is going to do is going to determine how many stochastic fault extension algorithms are essentially run, or how many cases of the fault extension algorithm are run in the background here whilst we're doing the calculation. So what Ava Structure is doing now is calculating that fault throw extraction directly from my interpretation data for each fault horizon input. And it's running a stochastic regression analysis for each fault tip, for each of my faults within my interpretation data set. So it's calculating that in the background, and then it's going to present me with my results in this interface. And just whilst it's doing that, I'm just going to introduce the data a bit further. You can see that I used a version 1 interpretation in here. I have a version 4, which essentially represents a more mature version of my interpretation. So the version 1 is sort of a poorly constrained auto track. It's maybe from a legacy volume. The version 4 has a far greater or far better constrained auto track in here. And I also have a set of more faults. So you can see my version 1, sparsely populated, the data isn't very well constrained, but my version 4 has a lot tighter auto tracking and is far better constrained around the faults. I also have a secondary folder here that contains some sub-fault interpretations, sort of the more minor faults within my interpretation. Okay, so it's often advantageous to have Ava Structure sort of open, paralleling a 3D window, but just for the purpose of this demo, I'm just going to expand it and run through the interface here. Okay, so the first thing that Ava Structure has given us is a quality assessment. So we've been given a score in here, and it's gone through and it's highlighted each of our faults within our faults folder, and it's given them a severity and also a comment as to sort of a quality assurance comment as to work that could be done to improve it and the impact that this has on potentially calculating the compartmentalization. So here, most of the things are telling me that there's too few throw data points to create a meaningful regression analysis. Go back and reinterpret this fault. But things like this one is telling me that my fault has increasing throw towards its end, so we have to assume a maximum uncertainty in here. Again, an area to address and go back and look at. But this map in here is interactive. I can toggle these on, and all those interpretation markers are sitting in my map in here. So it's telling me the same thing in my list, but I'm being given a score that can tell you basically how confident am I in my interpretation. Okay, and this map is interactive, so I can select one of these faults. If I come down in here, you'll see that we have those fault length against fault throw profiles. And we've calculated it for the whole fault, but obviously as this is an immature interpretation, it's missing parts of the data. And what we're concerned with is how Ava Structure is projecting and calculating our fault tip extensions and what the range in those extensions are. Let's go back up to my map. You can also view the fault throw on the fault maps in here. So I'm just going to zoom in and just focus on this one fault. And you can see that as we saw with the image of the Moab fault previously, we have calculated throw point data all the way along the fault, if you follow the cursor on the map, up until approximately, in this case, about 10 to 15 meters, which is where we've hit the limit of our seismic resolution. You can see from the map in there that this is where the data stops, but that red marker corresponds to the projection of our P50 fault tip. And what we're doing here is we're doing a linear regression analysis, and we're pushing through all these data points. So it's purely data driven. And then based on that number of cases that I specified, the stochastic realization in here, we populate this probability density curve in here. And that's telling us then how does that fault tip change in its 0 meter intercept based on my input data. So if we just look and flip between the P10, sorry, you can see that my data stops here, my fault tip now intersects here, my P50 and my P90. Now, obviously, this is a relatively benign fault. There's no intersections in here. It's not acting to compartmentalize my reservoir because the distance from which it intersects another fault is too far. But let's just zoom into another fault and look at the other features that we get out of Ava Structure. You'll notice that I said I want to rank my recovery cases by full field number of fault blocks. Then in each of these realizations, I've given a total number of fault blocks in here. So my P10, I have 4 blocks, and my P90, I have 13 blocks. And we can go in interactively and look at this map. And we're reporting the connected, or the total connected area for this compartment within here. So in this case, I've got 163 kilometers squared of connected area in my P50 case. Internally, I'm breaking up the field into these smaller compartments within here, but the main area of the field in here is in connection. If we were thinking about draining this area of the field, we could probably have an up dip producer and maybe one down dip injector, and that would perhaps do for the entire field. We start looking at the total number of wells to drain the whole compartment, and we start needing to refine the interpretation and looking down into here. And if I just zoom in to this fault in here then, look at my P50 case, I'll start with the P10. So you can see from the P10 that the connected area is 30 kilometers squared in here. This whole compartment is in connection. And you can see from the regression analysis that the P10 is picking out our fault twippers here. And the rules with these fault throw profiles is that we will see a linear regression basically to a 0 meter intercept unless the displacement that is being lost here is accommodated by another intersecting fault. And that's exactly what we see in our P50 case in here. You can see that Ava Structure is telling us we haven't hit the 0 meter intercept, and therefore we have a branch line. And that is the point at which we connect up to this fault in here. And that then in our P90 case gives us this compartment that's now split into 2, even 3. So in our P10 case, this whole area was connected up, but based on that linear regression analysis of our throw profiles, which is purely driven by our interpretation data, we're now splitting that up into 1, 2, 3, 4 individual compartments. Okay, we also have the number of cases here output as a histogram. So again, that stochastic realization, the number of cases that we specified when we ran the initial assessment, have now been represented here in this histogram. So we can see that we range from, again, 4 to 13 with a P10 to P90 ratio here essentially. And obviously, even though the number of fault blocks is quite low here, totaling 13, the range is quite wide. The range between the P10 and the P90 is quite wide, suggesting that there is a greater uncertainty associated with this. Now, the P50 and the P90 are quite close together. So maybe if we were to take this forward, we'd want to represent something maybe in the middle within here. But as you recall, we initially used that version 1 interpretation. We had that sparsely populated data, and we've also been told that our quality is relatively low. We have pretty low confidence in our interpretation. So this immediately is telling us to go back and address some of the issues, combined with the P10 to P90 ratio, saying that there's a high uncertainty associated with that. So the other thing that I can look at is the area connected to a well or location. So in here, you can see I've just specified the AMN01 well. I can add any well in here. But what that then reports in our cases is, rather than giving me a total number of fault blocks, I have a connected area. So our recovery case in this instance is showing us now a P10 to P50 distribution, but based on that connected area. So let's just have a look at what that's showing in map view then. This is our P50, and it's telling us that, as we saw previously, this well is only connected to, it's bounded by these 4 faults. Again, based on that faulted extension in here, it's bounded by these 4 faults. Now the P10, we switch to that. You'll recall that that 0 meter intercept fell short of the branch line with this fault in here. So it's opened up the entire compartment, and it's done the same thing on this fault in here. We just zoom in. It's telling us that it's hit a branch line at that point, but then the compartment has been closed up in our P50 case. So something to note in here is the range in the P10 to the P90. Again, we're looking at the connected area rather than the number of fault blocks, but we have a ratio of about 3 to 1. So it's not too bad, but if we want to really get a handle and be confident in our interpretation, we want to sort of see this reducing. But as I've said, we're using that version 1 interpretation. So let's go and run the same analysis, but using a more mature version of our interpretation. So all the interpretations that I've run, they sit within this interpretation assessments area. You can see a whole bunch that I've run today. But what we're using here is that version 4 horizon and all the faults, the fault folder in here. So I can either choose to show it within there, or I'm going to go back and ask to drop it in here. So Ava Structure 4, version 4 auto attract. Let's just open that. Okay, so the first thing we're going to look at then is that quality assessment and see how that confidence that we have in our interpretation has changed. And then we'll go and look through the total number of fault blocks, the P10 to P90 ratio, and then start looking at whether we can take some of these scenarios forward to something like modeling. There. So this is our version 4 interpretation and our main faults. You can see we have a better constraint in here, and some of that internal architecture has been better defined. It's still a bit noisy and a bit chaotic. It obviously doesn't need a perfect interpretation, but we also have a series of subfaults within here. Okay. So again, it's just gone through and it is now presenting me the results that we saw for the initial interpretation, but in this case for the version 4, that better constrained horizon interpretation. Okay, so let's start then by looking at that quality assessment. You can see that our score's gone down. We have a better confidence in our interpretation. And in this case, instead of telling us that there's not enough data to produce a meaningful regression analysis, it's telling us that we have to assume maximum uncertainty based on the throw profile. So it's calculated the throw profile data, it's run the regression analysis, and it's giving us QC markers as to how we can address those issues. So let's just close this off, and then let's look at the number of fault blocks. And immediately you'll see that by introducing those subfaults, we have a significantly greater number of total fault blocks within our field. So we're now ranging from 22 to 31. We look at that in histogram view. Now, although the total number has increased, the range has come down. So we're ranging 22 to 31 rather than sort of 4 to 13 in the last case. You can see that within here. So if we were to take some of these to go forward, we might be happy with just taking the single base case, or we might start to analyze something down in here. But again, we have connected areas within our interpretation. And if we start looking at the fault blocks we saw previously, we've included those sort of lower resolution faults, and we're really starting to segment up our reservoir in here. Thinking about total well counts, we went from this whole area in our P50 case and being connected, and now it's split into at least 1, 2, 3 main compartments. So we're doubling, tripling, even quadrupling the number of wells that we're going to need to drain this field. Okay, so we also looked at the area connected to the well. Let's go in here. So it's the same well, but obviously we now have these faults that are connecting up and really reducing down that area. So our P50 has come down because we're losing this area. Our P90 doesn't change because this fault doesn't have significant enough throw at its tips to project it and segment it even further. But our P10 has essentially excluded this whole compartment. We're now saying that we're going to completely close off this compartment based on that linear regression analysis of this fault. It hits the branch at that point in here. So looking at that histogram then, our P10 to P90 ratio in here when we saw sort of 3 to 1 in the initial case in our version 1. We're now looking in our version 4 case of sort of 2 to 1 or 15 to 6.5. So two things to take out of that is that our score has decreased, so our confidence has gone up in our interpretation, but also the uncertainty has narrowed as well, because we can see that range reducing. If I go back to looking at our full field number of fault blocks, if we're talking about uncertainty and analyzing this, we can start, as I said, choosing whether or not we want to take this structural configuration or the structural model further. If we feel fit, then we might want to sample something in here maybe, or maybe something in between the P10 and the P50, and take these forward to modeling. But Ava Structure is designed that you can run this analysis using purely interpretation data. I've not gone anywhere near the modeling domain just yet. I've just taken my horizon and my fault interpretation data, and I've already got a handle on what's the total number of compartments, what's the likely area, what's the average well spacing that I'm going to need, etc. So it could be used as sort of an assurance or a QC to aid sort of those exploration or new venture discussions. But as we mentioned earlier, it also complements the modeling workflows. So you can see that each one of these cases has an option to export my my fault sticks. I'm just going to do that now, and what that's essentially going to do is that's going to create a connected fault network based on the fault tip extensions. So anywhere in my P50 case that I see this linear regression analysis telling me that I'm going to extend my fault to here and then connect this up, it's going to build that connection for me and create me a set of fault sticks that I can use to take forward through to the modeling process. Now, the obvious thing before we want to do that is looking at the difference between these numbers here. So the fault tip extension that we're observing in this fault here, based on the fault flow profile of sort of 1,500 meters compared to the default in Petrel, which sits at 50. And that could be said for almost all of the faults, even the sort of isolated faults in here. You select one of those, we're still saying that the minimum extension is going to be sort of 400 meters in there, when in Petrel, the defaults that sit in there are telling us to extrapolate it by 50. Okay, but obviously exporting it in this way, we don't need to go through any of those extensions because Ava Structure is calculating that for us already. I'm just going to close this down and then take you through how you can use the output of Ava Structure as an input into the structural modeling workflows. Okay, so let's just see what this is, what it outputs. So you can see its names. Ava Structure using the horizon, and then it's telling me whether it's the P50 or P90. So in this case, the P50, I'm just going to turn off the interpretation, just zoom out, and you can see that we now have a regular spaced set of pillars, and they're connected in all the appropriate ways across these faults, including the horizon branch lines in here. So it's built up that interconnected fault network, and that is essentially good to go into the modeling process. If I just turn on maybe my interpretation data, you can see that it's a bit all over the place. The sticks aren't parallel and not regularly aligned, but in the background, Ava Structure has gone through each one of these faults, amended them, and then applied the connections for us already. So this can then be used directly into things like the structural modeling or structural framework building processes. And the reason that I'm using Petrel 2018 is to demonstrate how you can use the new functionality of depot grids to build up these multiple complex scenarios. So I'm not going to actually run this this process, but I'll show you the workflow that I've used to generate these, which is thinking about doing, and on my other screen. So the fault framework essentially takes this as an input. We then build our model based on the horizon output data that we have in here. We calculate a depot space calculation, and then we can build a structural depot grid. So these ultimately feed directly into this process. It removes any of the need to run through things like pillar gridding. This is automatically being done for us. So I've run this, this is my P50 case, I've taken my P10 and my P90 case, I've run it through this workflow, and I'm just going to show you the results just for one specific area around that well we were looking at earlier, the AMN 01, and just show you the difference between using the raw input data and the P10 5090 cases that are output from Ava Structure. So there's 4 screens here, they're camera linked, so it might take a while just to wake up. But as it's doing that, then obviously I am using Petrel 2018 because we can use the depot grids, but these outputs essentially can run straight into any structural framework builder. So they go straight into the process, and you can utilize the output of Ava Structure to build your structural grids. Should you be using Petrel 2018 though, these are an example of those depot grids. You can see I've got my raw data in the top left. I've got my P10 extension in here. I've just labeled the fault tip as a point in here. P50 case, we've nearly doubled the fault length, and then the P90, we're essentially closing off this entire compartment. And it's done it for all the faults automatically for me. It requires very little, if any, modification of the horizon interpretation because that's output directly for us. Okay, and then the final thing that I'm just going to show in this demo is the structural framework. So obviously the workflow would be to generate your horizon interpretation, run it through Ava Structure, then take the output into a structural framework builder, and then utilize that to build the depot grids. But I'm just going to go back now and show some top structure maps that were generated before those depot grids. So it's the input to the depot grid basically, and just to see what Ava Structure was calculating for us. Okay, so if I just turn on my models then, you can see that these are the outputs from that modeling process. These are my structural frameworks, and then from these, I just convert them to depot grids. So this is what we were seeing in the previous view, and now these are just some top structure maps showing the raw input data on the top left, moving through to the Ava realizations. If you try and flow, for example, from this down dip area in the raw data, you struggle, you have no issue, flowing up and through this compartment, through the well and up into the up dip area. Now, just by adding the P10 extensions, you can see that we start closing up this compartment here, and we've nearly, well, it's more than halved the total area connected to this AMN01 well. The P50 even more, and then the P90, we really start reducing that area. It's now confined to this little fault block within here, and we split this main area into maybe 1, 2, 3, 4, 5 fault blocks, and it wouldn't take much to push this through in here. Okay, so that is the workflow that can be used. I'm just going to jump back into PowerPoint. My computer's very slow now. And just show this. So obviously, as I said, it can be used to build it through the workflow. It can also be used as that sort of reference or validation tool at an early stage of the interpretation. So here you can see the seismic interpretation. Ava Structure fits in nicely to just basically take those interpretations and validate them, output a P10 5090 case that feeds directly into the structural framework process, and then we use that as an output to build our pillar grids, our stair step grids, or in Petrel 2018 we can build our depot grids. So you can really start integrating that uncertainty through the entire workflow and then take it forward to the modeling domain. Okay, well that's it for the presentation. So we'll open the floor to any questions.
Excuse me, sorry. Dan, thank you for presenting to us today. It's been really great to see how Ava Structure can help us address the limitations in structural modelling. We'll go ahead and take some questions now. Just a reminder for the audience that if you'd like to ask a question, please make sure you type it in the question box and you'll go to webinar control panel. You can also use the raise your hand option if you wish to join the discussion verbally instead. If you have any questions, now's the time to put them to Dan. We already have a question, and the question is as follows. How do you incorporate the horizon uncertainty as well as the fault uncertainty?
Okay, that's a very good question. Now, obviously, the horizon uncertainty is something a bit different to what we're talking about in terms of compartmentalization. The horizon uncertainty can be incorporated through things like depth conversion workflows, projections towards the faults, which we can do, but ultimately what we want to know is where those fault connections are before we start looking at the horizon uncertainty. So obviously when you're doing step out distances and removing the data away from there, we'd recommend doing as little of that as possible, and then building your uncertainty around that, and then making sure you have the connections in place before you start flexing the horizon interpretation. So the horizon interpretation in this case is used to calculate the fault throw, but Ava Structure is directed at looking at the compartmentalization within there.
Great, thank you, Dan. We have another question, which is regarding the quality assurance. Our audience wants to know what it is and how it's actually calculated.
Okay, yeah, so that's another good question. So that's, well, first of all, to note that this is looking specifically at the interpretation issues. It's not the modeling issues, such as the ones you'd see in Petrel. So it's essentially identifying any areas within our interpretation that either are telling us that it's going to have a significant contribution to the compartmentalization uncertainty, or that there's not enough data to get a meaningful calculation. So they're QC tools to look at your interpretation, areas to focus on that, but then also to go through and when you have a good quality interpretation, to show you where the biggest uncertainty in your fault connection areas are.
Great, thank you, Dan. We've got a couple of more minutes for a few more questions, so if you do have them, please feel free to ask. It looks like there aren't any other questions coming in right now. So Dan, is there anything else you'd like to add before we wrap up?
No, just thank you all for listening, and well, I'm sure you'll mention the next slide, so I'll just skip onto there, I think.
Great. Well, thank you to everyone for joining us this afternoon. We really appreciate you being here. Just a quick reminder that the webinar has been recorded and that attendees will receive a copy in the next 24 hours or so via email. If you have colleagues who you think might be interested in this webinar too, it will make it available on our website as well in the next few weeks, so you can share that link with them too. And finally, if you have any questions about this webinar or about Ava Structure in general, please feel free to reach out to the Ava Structure team. Dan is today's presenter, and his email address is dan.hemingway@pds.group. And also available for discussion is Mark Verschuren, the Ava Structure product owner, and he can also be reached via email at mark.verschuren@pds.group. In the meantime, you can also visit the Ava Structure website. There's a contact form there if you want to use that to contact us, but it also has some information about how the application works and some other bits and pieces of information. Finally, we'll be attending AAPGA's 2019 in San Antonio at the end of this week and the beginning of the next. Our booth number is 1145. Most of the Ava team will be at the conference, so if you have questions about Ava Structure or indeed about our other products, Ava Clastics and Ava Saturation, you can find us at the booth. We are also launching shortly a website where you can book demos in advance, so please do head to our website for more information on that. And we'll also be hosting talks about all three of our products throughout the week during the coffee breaks. So if you're interested, feel free to come and join us. We'll be launching Ava Structure at 4 p.m. on Monday afternoon, and there'll be some drinks too. So we'd look forward to seeing you there. Once again, thanks everyone for joining, and we look forward to seeing you next time.